In the previous lecture, we learned that a giant black hole, equivalent in mass to about 4 million suns, resides in the center of our Milky Way galaxy. Now, most other big galaxies harbor similar and often even larger supermassive black holes in their nuclei. But where did these beasts come from? How do they grow? How do they form? And do they have any observational signature earlier in the universe? Well, it turns out that they do. Indeed, decades ago, astronomers suggested the presence of supermassive black holes in order to explain extremely powerful objects called quasars. Now, these monsters are feasting on large amounts of gas that glows with a ferocious power. Let me tell you about them in this lecture. Now, in the post-World War II era, astronomers developed radio telescopes with which they could scan the skies at radio wavelengths. And they were finding all sorts of strong radio sources. Some were quite obvious emitters of radio waves. For example, the Crab Nebula, a supernova remnant, might have radio waves coming from all sorts of energetic charged particles spiraling around in magnetic fields. Or this peculiar galaxy, almost looks like a collision between two galaxies, might well be a source of radio waves. But other regions of the sky showed nothing obvious, nothing peculiar, just a whole bunch of stars. And since the early radio telescopes did not have great resolution, great clarity, they couldn't pinpoint exactly where the radio waves were coming from. They could be coming from any of the stars in that region, or maybe even some optically invisible object. But in a few cases, astronomers eventually concluded that the source of radio waves was a star-like object. And here are 4 such examples, star-like objects that are emitting radio waves. We call them star-like because most stars don't emit all that much radio radiation. So they were quasi-stellar radio sources, or quasars for short. These particular ones come from the 3rd Cambridge catalog of radio sources. When astronomers took optical spectra of these star-like objects, they found very peculiar results. Different quasars showed various broad, strong emission lines at wavelengths that didn't form any obvious pattern. You know, like calcium or magnesium or iron, they form obvious patterns in optical spectra, but the quasar spectra didn't seem to fit any known patterns seen in laboratory gases. An example is shown here, where you just see all these undulations up and down, but with no clear pattern. Now, at the time, 3C273, the brightest known quasar, was a source of great mystery. And because it was so bright, it was relatively easy to get a really good spectrum of it. So, in 1963, Martin Schmidt, an astronomer at Caltech, used the famous 200-inch Hale telescope at Palomar Observatory to obtain an optical spectrum of it, a high-quality optical spectrum. Now, using the 200-inch telescope is a wonderful thing. I've used it many times before, did my graduate thesis on it. It really makes you feel small because it's such a giant thing above you, just huge. The most powerful telescope for many decades. Now recall that a spectrum is what you get when you pass the light through a prism or a similar contraption. You spread the light out into the component colors, and generally you can see narrow little absorption lines from stars, but in the case of quasars, you had these broad emission lines. And in particular, the spectrum of 3C273, shown here, has these broad emission lines that again didn't fit any clear, obvious known pattern. However, Martin Schmidt stared at this spectrum and realized that it is basically the spectrum of hot, by that I mean roughly 10,000 degrees, 20,000 degrees, hydrogen gas, but shifted toward the red, shifted to longer wavelengths by a full 16%. Now that's astonishing, okay? Because you'll recall in Lecture 3, my brief discussion of the expansion of the universe and the associated redshifts of galaxies. Far more details are described in my full-length course with the teaching company entitled Understanding the Universe: An Introduction to Astronomy. But you will recall that basically, if I have all these galaxies represented by ping-pong balls and space is expanding between them, then all the galaxies move away from all others, and the more distant ones move away faster than the nearby ones because there's more space between the distant ones and yourself than between the nearby ones and yourself. So, redshift, or speed of recession, is proportional to distance. This is true for basically all galaxies except for those that are so close together that they are gravitationally bound to one another. All right, well, the spectra of nearby galaxies have a small redshift. The spectra of distant galaxies have a big redshift. The large redshift, 16% of 3C273, suggested that it was about 2 billion light years from Earth. Yet it was bright. You can actually see it in a relatively small telescope. So this was a giant surprise. Here's a bright object, 2 billion light years away. Most galaxies at that distance look really scrawny and faint and fuzzy. So this was a huge shock to the astronomical community. Martin Schmidt, shown here, became very famous. He's at the left. He's sitting with Alan Sandage, one of the great pioneers of cosmology, one of the main people in the 20th century who studied the expansion of the universe. Schmidt's discovery of these quasars being so distant placed him on the cover of Time magazine in 1963. That's maybe not quite as good as being on the cover of the Rolling Stone, but hey, rock stars can only do that, and astronomers can aspire to Time magazine or Newsweek. All right, well, different quasars have different redshifts, but all are basically billions of light years away, yet very bright. So what are they? Well, as I said, the discovery of quasars just rocked the scientific community, the astronomical community. There was a firestorm of activity in the mid-1960s and the late 1960s to try to figure out what these things are. How could objects of such high redshift appear so bright compared with faint galaxies at similar redshifts? You look at 3C273, it's this bright star-like object. At a distance of 2 billion light years, a few galaxies were known at the time, but they were very faint, fuzzy, barely visible in the world's best telescopes. 3C48 was another well-known quasar at the time. Its distance, computed from the redshift, was about 4 billion light years, yet it's visible through a moderately sized telescope. Just unheard of. Well, modern surveys of the sky have found over 1 million quasars. The Sloan Digital Sky Survey, for example, and the 2-degree field galaxy redshift survey conducted in Australia have just found lots of these things all over the place. And some of them have redshifts that place them at such big distances, 13 or 12 billion light years, that we see them as they were when the universe was only 7 or 10% of its current age of 13.7 billion years. And here's a picture of one of the most distant quasars seen when the universe was only 7% of its current age. Well, quasars appear star-like, smaller than galaxies. So physically, it's quite clear they're pretty small. But just how much smaller than galaxies are they? Turns out they're tiny. They're really, really tiny. And the way astronomers figured this out was by observing brightness variations of these quasars. If you plot the brightness of a quasar at radio wavelengths, for example, versus time, in this case for 3C279, you can see that over the course of years it grows brighter and fainter, sometimes by factors as much as, 100 or so. So why do they vary so dramatically? The fact that they vary over such short timescales and so dramatically means that they must be very, very small in physical size. Because consider the following diagram. If I have an object that's 1 light month in radius and it brightens intrinsically all at the same time, then light from the near side will have a 1 month head start over light from the side as viewed by us. It'll reach us 1 month earlier than the light coming from the side. Now, if the object is 1 light year in diameter and it all suddenly brightens, then light on the near side will have a 1 year head start and will reach us 1 year earlier than light from the side. Well, if you have an object that's 100,000 light years in diameter, like the galaxy, like our galaxy, and it all suddenly brightened, a distant observer would see the near side brighten 100,000 years earlier than the far side. So in other words, the time scale of variation is related to the intrinsic size of the object, rapid variations can only be produced by very small objects. And so quasars, varying on monthly or yearly timescales, couldn't be much bigger than light months or light years across. That's incredible, because they can be as powerful as 100 or 1,000 galaxies, having a size of 100,000 light years, yet the quasars themselves are only light months or light years in size, far, 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 far smaller than entire galaxies, yet hundreds of times more powerful. That is incredible. That is really, really incredible. It shook the world. What produces so much energy in such a small volume? Well, chemical energy is way too small. You can't burn a bunch of candles within one light month radius and expect so much power. It's just woefully inadequate. Even nuclear energy, the energy that drives the power of our sun and other stars, is not adequate. It has only 1% efficiency. That is, only 1% of the mass is converted into energy in the nuclear fusion reactions of stars. And you couldn't cram enough stars into such a small volume to generate the energy output seen in quasars. So by the process of elimination, what astronomers concluded was that quasars have gigantic black holes in their centers, 1 million to 1 billion, maybe even more solar masses. And those black holes are accreting, that is, swallowing the surrounding gases, the surrounding material. And in the process, that material falls toward the black hole, but it rubs against other material, and some of the energy of motion, the kinetic energy, gets converted into radiated energy. That process can have an efficiency of 10%, not just the 1% of the nuclear energy and even smaller percentage of chemical energy. So if a supermassive black hole swallows something like 1 to 10 solar masses of gas per year, then the conversion of part of that material into energy can drive the visible radiation from quasars. And the more luminous quasars devour gas at an even greater rate. So the stuff falls in, rubs due to friction, emits all this energy. The rubbing occurs because the gas is typically in an accretion disk, like the one shown here. The gas doesn't come straight into the black hole because it has some spin. Most clouds of gas are spinning to one degree or another. And so they settle into a disk, kind of like a protoplanetary disk, like the disk out of which our solar system formed. And that's where the gas particles rub against one another and release so much energy. Because the gas particles can clump up and, be non-uniform in their distribution, sometimes you have more apples falling toward the black hole, and sometimes you have fewer. By apples, I mean clumps of gas, of course. And so the rate at which radiation is emitted is not uniform. Well, that explains the observed light curves of quasars. They go up and down because of the variable accretion rate in the accretion disk. If the black hole is especially massive and is swallowing matter at unusually high rates, the light emitted from the gas in the vicinity of the black hole is so bright that it easily outshines the stars in the rest of the galaxy, making the galaxy itself hard to detect. That's why they appeared star-like. People couldn't see the galaxy. But now, high-quality images of relatively nearby quasars, those that are only a couple of billion light years away, reveal that they are embedded in galaxies. They're in the centers of galaxies. Here's one where there's fuzz and kind of looks like a galaxy. Here's another one where you see even some traces of a spiral arm. Well, they look like galaxies, but you can only really tell that they're galaxies if you obtain a spectrum of the so-called fuzz, the technical term given for the light surrounding the quasar. And the spectrum of the fuzz reveals absorption lines. In this graph here, the bottom line shows some absorption lines marked with calcium and magnesium. Those are absorption lines produced by elements in the atmospheres of stars. Stars make up galaxies. That spectrum looks very different from the spectrum of the quasar itself that's dominated by these giant, broad emission lines of hydrogen gas. All right, so the fuzz is indeed made of stars. Now let's examine the accretion disk again. Looking at this accretion disk, you can see that there's sort of a nozzle along which matter can be channeled in well-focused streams. Now, strong magnetic and electric fields are probably responsible for accelerating the charged particles to extremely high speeds. If the matter gains a lot of energy, some of that energy can push the material away, and it gets channeled, focused into jets along the nozzle, along the axis of rotation of the black hole and of the accretion disk, as shown here. This is reminiscent of the situation that we encountered for gamma-ray bursts, but of course on a much larger scale. You will recall that in gamma-ray bursts, material was pummeling out of a star along the axis of rotation because, again, that was the path of least resistance. That's where the particles can get out most easily. But a gamma-ray burst is very different from a quasar, despite this superficial similarity. A gamma-ray burst is associated with the formation of a stellar mass black hole, whereas a quasar involves a supermassive black hole in the middle of a galaxy. Here's an artist's animation of what might be going on in the middle of a quasar like this that's got an accretion disk that's forming a jet. Mind you, we've never seen this process in detail. That's for the future, but we can infer from the various clues that we've obtained that this is, roughly speaking, what's going on. We zoom in on the accretion disk. There's this funnel-shaped nozzle. In the middle, there's the black hole. And from the vicinity of the black hole, the matter gets ejected into these jets. Now, the most luminous quasars are extremely distant. Few are nearby. Quasars are denizens of the distant past, of the young universe. And in this photograph, taken by the Chandra X-ray Observatory, you can see a lot of bright X-ray bright points marked with all the little squares. These are powerful X-ray emitting quasars. Spectra of them show that they are very, very far away, billions of light years away. But as you can see in optical photographs, there's essentially nothing there. So sometimes the quasars glow most brightly at the highest energies, X-rays and ultraviolet. Indeed, in this picture taken with the Chandra X-ray Observatory, you can see so many bright points of light that are quasars of the distant past. And we can tell that the early universe was just filled with these things. And they're really very rare nowadays. So one might question whatever happened to them. Many or most of those points of light were accreting supermassive black holes. How did they form so early? You know, how can you form a billion solar mass black hole in the first billion years of the universe's existence? We're not exactly sure, but there's probably a lot of dark matter that you can't see, that tends to clump up, and that gathers material from its surroundings very efficiently, causing the black hole to grow. The other thing is that at the end of the previous lecture, I mentioned how black holes may have grown from seed black holes of intermediate mass. That is, black holes having only perhaps a few hundred solar masses or a few tens of thousands of solar masses. These may have been the seeds for growth. And recall that there is some preliminary evidence for such black holes in galaxies, especially in globular clusters. Now, a pretty massive example, having 40,000 solar masses, was recently reported in the giant globular cluster Omega Centauri, though the case is not yet fully settled. We're not sure that these globular clusters have these intermediate mass black holes, but we think they exist. So here's an artist's view of a black hole in a globular cluster, this dark spot surrounded by all these distorted stars. I'll tell you later why they look distorted. Anyway, from these seed black holes, you could grow bigger ones. When small galaxies having intermediate mass black holes merge together with time, forming bigger galaxies, well, then the black holes merge and form more massive black holes. The bulges of the merging galaxies also merge and form bigger bulges. This process was very efficient in the first few billion years of the universe's existence. Thus, supermassive black holes formed quite quickly, consistent with the Chandra image, showing many quasars in the young universe. A bunch of these merging galaxies came together, and their smallish or intermediate mass black holes came together and formed bigger black holes. But the growth of supermassive black holes also regulated the star formation rate to some extent. Powerful jets of particles from the black holes injected large amounts of energy into the surrounding gas. Here you can see an artist's animation of this process. You've got deep inside the galaxy, a black hole emitting these jets of particles. The particles hit the gas in the surrounding normal parts of the galaxy. That heats the gas and prevents it from coming in closer to the central region, closer to the bulge. So this prevents more and more bulge stars from forming. Also, there are rapid particle winds that blow off of the accretion disk, injecting additional energy into the surrounding gas, pushing that gas away from the bulge region. When we take photographs of quasars, we can see X-ray emitting lobes of gas that were clearly ejected from the central region. And here's an artist's impression of what's going on. You've got this accretion disk from which there's a wind of particles glowing at ultraviolet and X-ray energies, and these hot, energetic particles heat the surrounding gas, push it away from the central region, and thus limit the formation of additional stars in the bulge of the newly merged galaxy. Only some star formation will have occurred before the injection of energy partially quenches the star formation process. Well, this could partially explain the strong correlation between supermassive black hole mass and bulge mass that I showed in Lecture 5. You will recall that the bigger bulges have the bigger supermassive black holes. Smaller bulges have small supermassive black holes. This could be part of the explanation. Bulges were prohibited from undergoing rampant growth during the merging of smaller galaxies because energy injection from the supermassive black hole pushed the gas away. However, though this may be a good fraction of the explanation for the correlation, there may be other, still unknown factors that are partly responsible for it, so we're not quite sure yet. It's interesting that, in fact, this very same phenomenon of energy injection from jets and from winds from the accretion disk may have contributed to the demise of the luminous quasars. After all, these energetic outflows remove surrounding gas from the central region, okay? The region that's feeding gas into the central supermassive black hole. So if you remove the food, the quasar's not going to eat. It only glows while it's swallowing gas. Visible energy is emitted only at the expense of gravitational energy of the infalling gas. If there's not much infalling gas, there won't be much gravitational energy released, and so the disk, whatever disk is there, won't look bright. So this fading is consistent with the fact that quasars are most plentiful at great distances. We see them as they were long ago, when the universe was only a few billion years old compared with its current age of 13.7 billion years. Some of the quasars that we see nearby have been rejuvenated, in fact, because they are interacting or merging with other galaxies, and this helps drive gas back toward the black hole where it can glow while being eaten. You can see photographs of relatively nearby quasars rejuvenated through these interactions, gravitational interactions and merger events that drive gas, a fresh supply of gas, toward the black hole. Well, we also see many examples of less luminous versions of quasars in nearby galaxies. These are known as active galaxies or active galactic nuclei. Here's a rather bright one, almost qualifies to be a quasar, although you can relatively easily see the surrounding galaxy. But here are photographs of a more typical looking active galaxy and a normal galaxy at about the same distance. You can see the normal galaxy has a brightish nucleus, but not super bright, whereas the active galaxy has a much brighter nucleus. Something very energetic is going on in that galaxy that's not going on in the more normal galaxy. Well, this unusual activity is undoubtedly associated with accretion of gas into a supermassive black hole. For example, we can tell that the gas moves around very rapidly in the central region, as though it were being pulled by a supermassive black hole. You can see speeds of over 10,000 kilometers per second, and those are revealed by these broad emission lines. The emission lines are broad in an active galaxy and in a quasar, compared with comparable emission lines in a normal galaxy, because the gas is moving every which way, and those particles that are moving toward you appear blue-shifted, those particles that are moving away from you appear red-shifted, thus broadening the line. You also see radio and X-ray and optical jets in some of these active galaxies. I've mentioned M87 several times already. Peering into the core, you can see a jet of energetic particles moving at nearly the speed of light, emerging like from a fire hose in the middle of this galaxy. And Centaurus A, that funny-looking galaxy I showed you near the beginning of the lecture, has an X-ray jet coming out of it. Also, the jet is visible at other wavelengths. So a supermassive black hole is present in nearly each galaxy. Some are active because they're swallowing a little bit of material. They're munching slowly. Quasars are munching, well, voraciously eating. They look a lot brighter. But they were denizens of the distant past. They faded with time as they used up the material in their immediate surroundings and as the winds and jets blew the remaining material away. Quasars use up their fuel in about 10 to 100 million years. And a majority of massive galaxies have supermassive black holes within them. So given the number of observed galaxies and the number of observed quasars, it's actually quite reasonable to conclude that most galaxies at one point, probably early in the universe, went through a quasar-like active phase. Again, interactions help fuel the activity. Here you can see two active galaxies interacting with one another. Both of them produce jets. Those two galaxies should merge within a few billion years, forming an even bigger galaxy. Meanwhile, the supply of gas near the supermassive black holes in their centers is being replenished, so they display additional activity, specifically in the form of rapidly moving jets. And in this artist's animation, we'll zoom in on one of these pairs of merging galaxies to see what's going on. There's one galaxy. Now we'll see the other one come into view. They're much closer together than our typical galaxies spread far apart throughout the universe. These guys are not expanding away from each other due to the expansion of the universe. Rather, they are gravitationally pulling each other in, and they will someday merge, okay? And that merging event helps fuel additional activity. Here you can see gas being eaten up by a central supermassive black hole. And in an artist's impression of what the whole process is, we're going to look down into the heart of this Centaurus A galaxy, this weird, dusty, peculiar-looking galaxy. Let's peer down into the central region at infrared wavelengths, where the center is easier to see because it's not so blocked by other gas and dust. Peering down farther in. Again, I emphasize, we've never actually seen this, but this is what we infer to be happening. We can see this jet coming out. And there is evidence for the jet. We just haven't made a movie of an actual active galaxy of this sort, okay? And we've never quite seen details like those shown by the artist. But we think this is a pretty accurate representation of what goes on in an active galaxy that's merging or interacting with another galaxy. Okay, well, if you accrete rotating material, the black hole should spin up. As the stuff falls closer to the material, to the nucleus, the stuff spins up even more. Jets are a consequence of this spin. Basically, if we measure the spins of black holes, we should see that they are indeed spinning. Well, in fact, exceedingly rapid speeds have been measured near the centers of some galaxies, that is, near the supermassive black holes. You can see gas glowing at a much greater rate than would normally be the case. You see, normally it would be glowing at some rate if it were around a non-rotating black hole. But near a rotating black hole, the gas can tap some of the spin energy of the black hole and glow much more brightly. Just as I said in Lecture 1, how a garbage truck can go into the ergosphere of a spinning black hole, dump some of the garbage in, and emerge with greater energy compared with that with which it went in. So gas near a spinning black hole can tap the rotational energy of the black hole and thus become more energetic, glowing much more brightly than would have been the case if it were near a non-rotating black hole. Look at that gas glowing there, very, very brightly. There's additional direct evidence for spinning accretion disks from recent XMM Newton X-ray telescope observations of the region near a supermassive black hole. You can see blobs of gas in the accretion disk, as shown here from the artist's animation. And these blobs are moving at over 10% of the speed of light. You can tell this because as the blobs come toward us, the radiation is blue shifted. As they move away from us, the radiation is red shifted. And from the amount of the shift, you can tell that they're moving at over 10% of the speed of light. That gas gets accreted by the supermassive black hole. Rotation is conserved, so that must make the black hole itself spin faster as well. And there's additional X-ray observations of the detailed shapes of emission lines coming from that gas surrounding the black hole that shows that that gas is spinning very rapidly, and so the black hole itself that's accreting the gas is likely to be spinning rapidly as well. This suggests that these particular black holes grew mostly by accretion of gas from the disk rather than by merging with other black holes, because we see some of these black holes spinning at nearly the maximum possible Einsteinian rate, nearly the rate at which they would spin if the event horizons were to merge together. So with slightly more spin, some of these black holes might even have horizons that vanish, leaving a naked singularity. Wouldn't that be amazing to see? Well, you can refer to this as a voracious vortex, ravenously devouring the matter in its vicinity while spinning faster and faster and shooting some of the gas outward at nearly the speed of light. Wow, that's just amazing. So we've seen that quasars are the most powerful objects in the universe over timescales of millions of years. As their supermassive black holes devour the surrounding nearby gas, they gradually fade, turning into more normal-looking galaxies. And even starving supermassive black holes, having been deprived of their fuel, can be rejuvenated when the galaxies in which they live interact and merge with others. What would the direct observational signature of the coalescence of two giant black holes be? We will see in the next lecture that the answer is gravitational waves, ripples in the very fabric of space-time.